Okay, this is one of the suggested problems from chapter 4, problem 470. Here we have a 75 kilogram person that stands on a scale in an elevator. What does the scale read in newtons and kilograms when the elevator is at rest? The elevator is climbing at a constant speed, descending at a constant speed, the elevator is accelerating upward with a constant acceleration, and it accelerating downward with a constant acceleration. So let's start with the simple case. Okay, so we have a scale, and we have a person standing on the scale, and this person's mass is 75 kilograms. 75 kilograms, and this person is just standing on the scale. What will the scale read? Now, what does scale read in general? The scale actually reads the normal force that it applies on the person or the item standing on it. Okay? So this person is at rest. It has no acceleration, which means that the total mass, the total force acting on it must be 0. If you draw the free body diagram, this is Fg, which is of course equal to m times g. That must be exactly compensated by the normal force, which also must be equal to mg, equal in opposite direction. Okay? So this, what you read on the scale is normal force, so you will read mg, so 75 times 9.8 newtons, or most scales are given in kilograms, you'll just simply read 75 kilograms. Now what does happen if this person is actually moving down with some velocity, 3 meters per second? Okay? Well, nothing will change. It's moving down with constant velocity. The acceleration is 0, which means that the net force is still 0. So this still holds. You will just read the same thing on the scale. The same argument applies when it's moving up with a constant velocity. There is no acceleration, so the net force is 0. The total force must be cancelling. These are the only forces available to us. And then we will just get the same reading on the scale. Now the money problem, or the money question, is what happens if I have an acceleration, let's say going down, okay, of 3 meters per second squared this time. Okay? I'm accelerating downwards. Now, in this case, first of all, you should solve this problem in the inertial frame. Okay? You should not say that, okay, because of the acceleration, there's some fictitious force, and add this to the free body diagram and so on and so forth. That will be wrong. If they're asking for the free body diagram, that will be wrong. The free body diagram involves only the forces acting on the object, and fictitious forces are not counted. Okay? You're talking about the acceleration. It means that you're in the inertial frame. You are seeing the elevator accelerate. Inside the elevator, there will be a fictitious force because you're not seeing the acceleration. For you to accelerate, the elevator will not be accelerating. Okay? But there will be something. You are outside. You're given the acceleration. So you should solve this in the inertial frame. And in that inertial frame, these two are not going to cancel. Okay? These two are not going to cancel. In fact, their difference is going to lead to this acceleration. Okay? And now you can easily say that, okay, normal force is going to be mg minus ma, and perhaps this was something you know already. If the accelerator is accelerating down, then you feel less weight. You feel kind of sort of weightless, and so you will read smaller number on the scale. And if the acceleration, if the elevator is accelerating up, then again, this difference is going to, I'm being a little bit sloppy here with the signs and everything, but it's of course possible to be more formal. The aim of this problem is to show that it can be solved in the inertial frame. Right? But let's try to be more formal. Let's draw the coordinate system with the x positive, and then we have an acceleration that's up, okay, by 3 meters per second squared. Now, how would you do it this way? Now, I have my gravitational force plus my normal force. This is going to lead to some ma. Okay? So now I'm writing this in vectors. This is the left-hand side is the total force. The right-hand side is m times a. This is Newton's second law. Okay, fine. Now, what is this one? If I write the x components, this is just going to be m times g I had with a negative sign. My g is always 9.8. This is going to be mass 75 times 9.8 with a negative sign because it's down. Plus, you know, Fn I had plus is equal to your mass times the acceleration is 3, but it's actually negative 3. Okay? So if you want to do it formally, you will do it this way. You will keep all your i's, we can actually drop the unit vectors, and as you'll see, the normal force is going to be something larger, right? How to get this? Sorry, the acceleration is up, so that's how we get it larger. I'm sorry. And Fn is going to be mg plus 3. Okay? So when you're being formal, you also have to be a little bit careful. I accidentally said that this is negative, but it's not. Our acceleration is up, and I've chosen up as positive. That's why the gravitational acceleration was negative. But you get your answer. Now, you can do this formally, informally. It doesn't really matter too much, but when you're drawing the free body diagram, you should not have a m times a force over here. You should not have a fictitious force. Okay? Other than that, I think that this is a very basic problem, so I'm not going to elaborate too much.